All right, let's talk about one of the most fundamental ideas in all of computing, CPU addressing modes. Think of it as the secret language your processor uses to find exactly where to look for data to get its job done.
You know, your computer's memory is just this massive, sprawling city with literally billions of different addresses. So when a program needs to grab just one specific piece of information, how in the world does the CPU know where to look? How does it find that one house on that one street in a fraction of a second?
Well, the answer is a concept called addressing modes. And honestly, the best way to think of them is as an internal GPS for your CPU. They provide the exact set of rules and coordinates for navigating that huge city of memory to find any location instantly.
So here's our game plan. We'll start with what these things even are. Then we'll check out the simple modes for data that's close by. After that, we'll see how the CPU reaches out into main memory, explore some really powerful modes, and then we'll actually walk through an address calculation to see it all click into place.
So, let's get right to it. At their very core, what are they? Well, addressing modes are just the specific rules a CPU follows to understand an instruction and figure out the final location of the data it needs to work with.
To get a little more formal about it, an addressing mode defines how an instruction specifies its operand, and an operand is just a fancy word for the data it's operating on. So really, each mode is just a different recipe for calculating the final memory address of that data.
Okay, let's start with the easiest cases, the modes that get used when the data is pretty much sitting right in front of the CPU's face. This one's called immediate addressing, and it is the most direct mode you can possibly get. The data isn't in memory, it's not even in a separate storage spot, it's literally baked right into the instruction code itself. No searching necessary. For instance, a command like Emu8086 tells the CPU to take the immediate value 1234H, that little h just means it's a hexadecimal number, and pop it directly into a storage location called the AX register. The data is part of the command. It's right there. Next up is register addressing. This one is incredibly fast because the data is already inside the CPU, tucked away in one of its super fast little storage spots called registers. It's kind of like grabbing a tool that you already have sitting on your workbench.
So here, an instruction like MOVAX doesn't have to go out to main memory at all. It's just a quick internal data swap. It tells the CPU, hey, whatever number is in the BX register right now, just make a copy of it and put it into the AX register.
Okay, but what happens when the data isn't already inside the CPU? Now we need ways to reach outside the processor and into the main system memory, or what you probably know as RAM.
And that brings us to direct addressing. With this mode, the instruction itself contains the specific memory address. It's like a command that says, go to 123 Main Street, the package you need is inside that house.
Now look closely at the syntax here. See those square brackets around 1234H? They are absolutely crucial. There's a signal to the CPU that says, hey, don't treat this number as the data, treat it as an address. Go to that location in memory, see what value is stored there, and then copy that value into the AX register.
Now, let's take it another step. This one's pretty clever. It's called register indirect addressing. Instead of putting the address directly in the instruction, we put the address into a register first. Then the instruction just points to that register. It's indirect, like being told, the address you need, I wrote it down on the note inside that drawer. All right, now we get to the really powerful memory modes. These are the ones that give programmers the flexibility to work with more complex things like long lists of data or arrays in a really efficient way.
You can think of these two modes like a filing system. Based addressing, which usually uses registers like BX or BP, points to the start of the whole data structure. It sets the base. Then you have indexed addressing, which uses registers like SI or DI, and that acts as an index. It tells you which specific item to grab from within that structure.
And you probably guessed it. When you combine them both, you get based indexed addressing. This is really the most flexible mode of all. It uses a base register to find the start of something, and an index register to pinpoint a specific element inside it. It's like your GPS calculating a route with both a starting point and a specific distance to travel from there. Okay, enough theory. The absolute best way to understand this stuff is to just see it in action. So let's actually calculate a physical memory address from scratch.
Here's our problem. We're given the values in 3 registers: the data segment, or DS, the base register, BX, and the index register, SI. Our goal is to figure out the final physical address for this instruction, which, you can see, uses that based index addressing we just talked about.
We're going to do this in 2 simple steps. First, we'll calculate what's known as the effective address, or EA. You can think of this as the offset, or the local part of the address. Then we'll use that along with the segment register to find the final physical address in RAM.
So for step 1, we just do what the instruction tells us to do inside those brackets, BX plus SI. We just add the contents of the BX and SI registers together. So 0150H plus 0010H gives us our effective address, 0160H. That's it for step 1.
And now for the final step. To get the full 20-bit physical address, we have to combine our segment with our offset. We take the data segment register, which is 2000H, and we do a little trick. We shift it left by 1 hexadecimal place. This is the same as multiplying by 10H, or basically just tacking a 0 on the end. This gives us 20,000H. Then we just add our effective address from step 1, the 0160H, and we get our final physical address, 20160H. That's the exact spot in our city of memory that the CPU is going to go to.
So let's bring it all home. We've seen all these different modes. We've even calculated an address. Why is this internal GPS so darn important?
You know, at the end of the day, this is the language the hardware actually speaks. And understanding these modes, well, it's the difference between just guessing what some low-level code is doing and truly knowing. This whole system is what allows all the software we use to work so efficiently, navigating massive amounts of data with total precision. Without it, our complex digital world just wouldn't be possible.